students, friends, alums, board members, faculty, everyone. Yeah, it's my pleasure to introduce Dr. Jim Donovan, better known as JD around here. As a member of he's been a member of the Shimer faculty since 1999. And started off with, I'm going to tell you a little bit about him and kind of my experiences a little bit too. Jim started his education basically off at the University of Notre Dame in chemistry, and then moved on for a PhD at the University of Chicago, at that point in biophysics and theoretical biology. After the years of study, some postdocs, and then he did something which probably is usual for many, not for others. He went into the private sector for a number of years and worked at Abbott Labs, doing research, hepatitis and AIDS, and also was a quality manager. I had no idea in those years he was living a few blocks from me, actually. And then he always wondered about that school along Sheridan Road. And when we had a job advertisement, I guess he noticed that there we were, and came to Shimer after a number of years. There's a point when he did something quite different. And he worked with, and I say with rather than for, because I think it says something about Jim, for Habitat for Humanity International. He was a regional training manager, although he'd already worked there for quite a while. I think this really represents, in large point, the community spirit and the commitment to community activism that is really a major part of Jim's life. He's been president of the Waukegan Downtown Association. He's been a board member and treasurer there. He's been president of Habitat for Humanity of Illinois in the past also. So a real combination of the academic world and Habitat for Humanity, a real commitment to service. What this tells us is that Jim doesn't fit the stereotype. I don't know if the stereotype really exists of this person who has no interest in people or the world, sitting in a lab, looking at whatever, studying a very narrow topic.
I wouldn't go that far.
You wouldn't go that far? Jim doesn't at all. He's been a people-oriented person. And in that regard, I think Shimer has offered him a wonderful place to combine both. His theoretical sciences and his interest in community, working with people and working with students. And his excitement about science is really contagious. I hear him, I see him talking in the lab, laughing. He's clearly a favorite among Shimer instructors. And yeah, it's wonderful just to hear him. And sometimes in lab coats, sometimes just playing around with various objects and pointing things out. In terms of this topic, he says, my grand obsession, those are his words, over dark matter and dark energy began after a lively discussion in a Shimer classroom more than 8 years ago. He also notes that this project has brought him away from his original area of expertise as he's progressed from biophysics to astrophysics. So today, he's going to continue to grapple with this question, what in the world is the what in the world? He's going to update us on his research into the existence of dark matter. And for those of you who know Jim, expect some humor. Jim loves to tell jokes, and I'm a very good audience because I can't remember any of them. You can tell me the same joke over and over, and I just laugh. Well, I shouldn't quite say that. Sometimes I laugh, and sometimes I groan. And I assume tonight, you will not disappoint. Thanks a lot, Jim.
I didn't know we were going to begin with a critique of my humor. I'll just point out that perhaps the greatest hitter, not the slugger is the home run hitters, but the most consistent hitter was Ted Williams, and his batting average was .401, which is astounding. I figure if 40.1% of my jokes are good ones, I'm Ted Williams. process about making a meditation about physics and mathematics and beauty as well. Because when I do science and I think beauty, I think them at the same time. So if I'm going to start talking about the university, let's set the stage. Let's get a feel for it. The universe, in case you didn't know, is really big. Would you be so kind?
Space is big, really big. You won't believe how vastly mind-bogglingly big it is. I mean, you may think it's a long way down the road to chemists, but that's just peanuts to space.
Douglas Adams, Hitchhiker's Guide to the Galaxy. Well, I just realized on several slides there will be something to read down here. So I'm going to ask those who struggle with me in the back, if you could just, we'll go on with the talk, but if you can nudge that up just about another foot, so we don't have to bother the back of anyone's head anymore. I want to give you another way to get not just words about how mind-bogglingly big it is, but a feel for it. Imagine holding a BB. And for those of you with a deprived childhood and your parents won't let you play with toy cars, a BB is about 1/8 of an inch in diameter. It's a little metal sphere, okay? Imagine holding a BB at arm's length, okay? And look up at the sky. There's not a whole lot of sky behind that BB, is there? Looking up at the sky. There's not a whole lot of sky behind it. Well, there's a very famous picture that was taken by the Hubble Space Telescope, the best telescope on Earth, or I guess technically not on Earth. And the operators of the space telescope, NASA, wondered just how far can we really see with this thing? Just how good is this telescope? So they took a picture, and to see distant objects, they picked a spot in the sky where they knew there were no stars in our Milky Way in that direction. It's a spot somewhere in the Big Dipper. And they focused the Hubble on that one spot, about the size of a BB at arm's length, for 3.5 months. Now that's time exposure. They wanted to get, no matter how dim it was, they wanted to see if they could get a picture of it. This is that picture. It's called Hubble Deep Field. Excuse me, Ultra Deep Field. I told you there were no stars in the direction of this. Every spot of light in that picture is an entire galaxy. There are 10,000 galaxies in that picture. There are 10,000 galaxies behind that BB. And how many BBs would it take to cover the whole sky and the half of the sky that you can't see at a time? How many trillions of island universes, to use an old-fashioned term for a galaxy? This thing we call a world is mind-bogglingly big. So let's break it down into smaller parts. Let's get at least a little bit smaller than that. Oh, well, first, how did it get so big? Well, it expanded. You've probably heard the universe is expanding. Anyone here seen the movie Annie Hall?
Yeah.
And you know the scene?
Yes.
Yeah. And when I saw Annie Hall, I'm sitting in the movie theater, and everybody's laughing at, for those of you who haven't seen it, it's the young Woody Allen. And his parents think the kid's going crazy because he's just freaking out. He can't stand with the anxiety. Kid, what's the matter? The universe is expanding. And you laugh. And I went to the theater. And everybody laughed. Except me. I knew how that kid felt. At the same age, I felt the same way. All right? So next time, have more empathy for the people suffering on screen, okay? And next team might be. The universe is expanding. Big Bang at the beginning. What was before that? I don't know. I mean, personally, I don't think the So time zero, Big Bang. Then the universe expanded very suddenly in what's called inflation. It kept expanding. Currently, it is, it looks like the expansion is accelerating, but it got really big. Let's look at a part of the universe. Oh wait, no, this is the whole deep field again. There's some stars in there, but the bigger spots in there are galaxies. This is called the Virgo supercluster. Some of the main members of it are here labeled. We are a member of the I don't have a membership card, but the Milky Way is part of the Virgo supercluster. This is a mere few hundred million light years across. This is the local group, or part of it, which we are part of. You can see it's closer. You can actually make out the shapes of the galaxies. Here's one member of the local group. One of my favorites. It's called the Sombrero Galaxy. And you can see the rim, and when it's not quite as heavily exposed, you can really see it looks like a sombrero. Physicists may not have good senses of humor, but they're great at coming up with cute names. Question, beautiful or not beautiful? I think it's beautiful. I think it's beautiful. Closer to home, this is the Andromeda Galaxy. This is the closest major galaxy. Ours looks a lot like that. Andromeda is our big brother. It's just a little bit bigger. Beautiful? Yeah, that's one of my favorites. Closer to home, well, this is home. This is the Milky Way. Of course, this is what it looks like from the inside. This is the sky showing the full expanse of the Milky Way. The dark areas are dust clouds between us and the bulk of stars in the direction of the center of the galaxy. We can't really get this perspective. This is what it would look like from the outside. From the side, if we looked on it, we've got dust too. Might look a lot like sombrero at this angle. There's a bulge in the middle where most of the stars are, but the stars go out in the disk. We're out, I'm thinking about this far out. And there's little globular clusters all scattered around. If we could get above, it would look something like this. And we're right about here in the Milky Way. It's home, I think. Here's sort of a rogues gallery of galaxies, just to give you an idea that they come in a lot of different shapes, flavors, sizes, though the main categories are elliptical galaxies, like this one, or this one, which are eggs or football-shaped objects of stars. And then there's the spiral galaxy, like our own, the Milky Way, or you can see this is a spiral galaxy, you can see the spiral of this one. And most of these, like this, that's a spiral, but you're looking edge on, so you don't see the ring surface, you just see the edge. Here's a nice picture, which shows sort of in one shot, these really are located near each other up in the sky. I forget the names of these. Oh, the light. That's a really nice spiral. Can we bring this light up? Oh, I think that's better. What do you guys say? So this spiral, an elliptical, and a spiral on edge. A few more as long as we're talking galaxies so you get a sense of what's up there. This is two galaxies colliding. There's a nickname. The mice. Can you see it? Nickname for this one, the tadpole galaxy. This is a nickname, but before I tell you, picture this thing diving. What would you call it? Diver. What? Dolphin. The nickname for this thing is the whale. agree on the name for this one. What's it look like? Yeah, the Friday Galaxy. Beautiful?
Yeah.
And it's a whimsical way. And my favorite, the Whirlpool Galaxy. When I think spiral galaxy, I think of this one. Sometimes I fall asleep at night thinking, I hope the people in the whirlpool look at our galaxy and think we're as pretty as they are. I have a boundary issue. Here's the element of my talk. The intro's over, I don't have to mention that. Now I'm going to talk about what the components are in the universe. What is the what that all of this is made out of? There's a problem and a puzzle that will emerge as I talk about what we think it's made out of. I will then summarize in layperson's terms my own, and I stress still tentative work, which makes use of facts like the universe is expanding, the universe had a beginning. You'll see that when I get into it, and then I'll sum up. Close. Beautiful? Isn't that amazing? Here's something to ponder, by the way. These are just hunks of glowing gas out there. We have evolved on the savannas of Africa. Why did we evolve to think that something like that is beautiful? I don't have the answer to that question. Back to galaxies. Where do they get this beautiful structure from? Well, gravity holds them together. That's held together by gravity. This, by the way, is called a barred spiral. Ours is thought to be not as extreme, but similar to this, where there's a straight bar, not just circle in the middle, and the spirals come off of that. Gravity holds that thing together. The way that works is the stars orbit the galaxy, or more precisely, orbit the mass of the other stars further in toward the center of the galaxy. Basically, it's analogous to the solar system. Most of the mass is in the middle. The stars in the middle rotate quickly, like Mercury does around the sun. The stars are a bit further out, not quite so quickly, like Earth, Mars. And then further out, like Pluto. Yeah, I'll call Pluto a planet just to be nice to him. Goes real slowly. And that should be the same thing going on in galaxies. We'll see in a minute. Yeah. In fact, weight, technically mass, is the single most important factor in controlling how the universe behaves and how the objects in it behave on a large scale. Small scale, electromagnetic forces dominate. Large scale, it's almost all gravity. That's the mass of the stars and planets, like the orbits of the solar system, the mass of galaxies, which controls their rotation, and even the mass of the whole universe. Well, how to figure out how much the universe weighs? First, you got a real big bathroom scale. No, that doesn't work. What you can do is you can do a cosmic census. Census is count what's out there. And in principle, it's easy to do. Did I flash that out? I'm sorry. I had to. I'll put it in my pocket when I'm done. From the light of the stars and the gas in a galaxy, you can calculate the mass of the galaxy. For good measure, you can look at the orbital speed of the stars, how fast the galaxy is rotating, and calculate the mass that way. Because the more mass, the faster something will, the stars will orbit, the faster they will rotate. You can also measure the shape of space itself. Now, that may seem like a really weird concept. So before I start talking about what the shape of space is, I just want to talk about shape for a second. As far as geometry, or more precisely differential geometry goes, There's flat, like the table. You've all taken. I got a lot of current and past Shimer students here. You've all seen Euclid and IS2, those of you who've gone through the core. And Euclid is the archetype of what happens on a plane, a flat surface. If you haven't gone to Shimer, you know, you can take IS2, we allow other students. It's a great experience. Those Shimer students, if you think IS2 was a great experience, tell the non-Shimerians how great it was with a round of applause. If you've not taken IS2, now you know you want to. That's Euclid. Also in IS2, they're negatively curved spaces. You remember Lobachevsky? What Lobachevsky is describing is like the surface of the trumpet. Would you hold this trumpet for a second? You know, hold it up for me. Because you know the crazy picture where he's got the two parallel lines that are getting closer together? Well, if I were to draw two parallel lines running down here, you can see they would be parallel. They would never reach if the trumpet was infinitely long, but they get closer and closer together. This is a Lobachevskian space, and it's negatively curved. Positively curved is something like this. Lines on this tend not to spread out the same way. Think for a second. On a flat surface, if I go in that direction and that direction, as I go out, I get the same distance apart as I go up. If I were to do that on the surface of a trumpet, the further I move along the trumpet, I would get apart, the two paths would diverge faster, right? Whereas on the Earth, imagine going at the North Pole and you go down one line of longitude, one meridian, and someone else goes down another. You don't diverge as fast because the Earth is curving in on you. So when you ask me, what do I mean when I talk about the shape of space? These are two-dimensional surfaces. We can all picture that. I can't picture a curved three-dimensional space, but we can still measure it just by looking at how lines, whether they diverge faster or less fast than we expect. Does that make sense? So the notion of curvature of space is a meaningful concept. And if we can measure the shape of space, we can tell you what the density is. And we can do it from the cosmic microwave background. When the Big Bang occurred, it filled space with light. And it's still there, or I should say it's here, outside the window. It was visible in ultraviolet when it happened, but the universe has expanded. The light has stretched. It's now almost all microwave frequency of radiation. It's called the cosmic microwave background. It's in every direction. It's kind of spotty. I mean, it's stronger in some directions and weaker in the others, but it's everywhere. And you may have seen it back in the old days when you didn't have a digital TV. Anyone here still have an analog TV? All right. You can double check this now. If you go home, pick a channel that no one's broadcasting on, and you see the snow. Most of that static is the cosmic microwave background. So you can go home tonight and watch the Big Bang live. And this is what it looks like. This is a picture of the cosmic microwave background. This is a map of the entire sky, all 360 degrees. And the spots are, I should say the color of the spots show the intensity. It's a little stronger intensity in the red and yellow, a little weaker intensity in the blue. And these are very small changes. It's really quite smooth, so these are exaggerating the looks. Beautiful or not beautiful?
Yeah.
You're looking at a picture of the Big Bang. Beautiful?
Yeah.
When this was first published, I forget the name of the scientist, one of the lead scientists on the project was interviewed, and he was just visibly bubbling in his excitement. And the interviewer, the reporter said, "Why are you so excited about this?" He said, "You don't understand. For me, this is like looking into the face of God," which shows how profound it can be for people. For myself, I don't see the face of it. I see his fingerprint. But beautiful, yeah, I'm with you. The cosmic microwave background. And the data, how the calculation is done, in fact, I would have to go look it up. If you asked me how, I couldn't repeat it for you in front of you. The data shows that the universe is very, very, very close to flat. Maybe even perfectly flat. Well, that's kind of cool. The reason is, it allows us to calculate the density of space. Now first, quick lesson in general relativity. General relativity, the key points in 30 seconds. Point number one. Mass bends space. You've probably heard that. Mass bends space-time, bends space-time, that's what causes gravity. Since it bends space, it leads to reason that the density of the universe, the average mass, will determine its shape. Okay? The flatness corresponds to a very specific density. And that density is given by the Friedmann equation, which I would read as follows. H prime over h quantity squared equals 8 pi g over 3 times rho. Got it? In English, the speed at which the speed is the wrong word. The rate at which the universe is expanding is equal to a geometric constant times the strength of gravity constant. It's called Newton's constant. Times the density of the universe. Well, we've known the value of these numbers for thousands of years. We've known the value of this gravitational constant for 200 years. This has been measured, in the modern era. And we know that, we know that, we know that, we know that. Oh my gosh, we can calculate rho. We know the average density of the universe. And then it leads to a problem. Doing the census and observing the gas and stars, the mass of gas and stars is less than 1/20th the amount of mass, which is the average density of the universe. That means more than 95% of everything in the universe is something, and we don't know what it is. Now, some people might think this is a failure, and this is a black eye. No one reacting? What do you think the nickname of this galaxy is? Yeah, you got it. The Black Eye Galaxy. This is a bunch of lanes of dust between us and the stars behind us. This type of, should I say, anomaly is not considered a failure in physics. It doesn't give it a black eye. In fact, it makes everybody really, really excited. Physicists love it when this happens. Because a lot of people say, well, scientists, they're the ones who love to explain things. But yeah, scientists do like to explain things. But what scientists really like to do is discover things. Richard Feynman, a name most of you have probably heard, one of his autobiographies is titled The Joy of Figuring Things Out. Figuring things, well, if you figured everything out, what the hell fun is it? But if there's something like, we don't know what's going on, yes, let's go figure it out. That is science in action. The interesting thing is, from a Shimer perspective, we're in the same physics. The cutting edge of astrophysics is at the same place as Thales was and the pre-Socratics that we read in Natural Sciences 1. We can observe the world's behavior. We don't really know what it's made out of. And we're not even sure how to figure out why. We can figure out how. In Natural Sciences 1, you learn, okay, it took a couple thousand years, but once we get through to the periodic table, we basically know that what the world is made of. I don't think I've taken this long this time, because we had some clues. Clue number one. When you look at the cosmic census, from the light of the stars and gas, we calculate the mass of galaxies. I told you that. From the orbital speed, we calculate that. I told you that. These two masses don't match. That is an interesting clue. Galaxies rotate faster than the mass of the luminous matter that they can account for. That thing is rotating faster than we think it should. And here, in fact, is some data. What this represents, this is a graph from Science Journal a few years ago. I forget the galaxy, I'm sorry. Here's what this represents. For different distances from the middle of the galaxy. So here's the center of the galaxy. This is about 100,000 light years away. This shows the speed, the velocity more precisely, with which the stars are orbiting the middle of the galaxy. Based on the amount of gas and stars that we measure by looking at through a telescope, we know where the stars are, we know where the mass of the stars are. This is the rotation that we would expect. This is what's measured. The stars are orbiting faster than we would expect based on the amount of matter that we can see stars and gas. That means there's something in that galaxy which is about 5 to 6 times as much of it as there are stars and gas. It's gravitational, it's sitting there, so it means it's matter. It doesn't interact with light. What are we going to call it? Dark matter. Which is actually a pretty good name. The name's been around for decades. We don't know what it is, all we know is it's sitting there and gravitating. So that thing, you see all these stars, the current consensus is that those stars are maybe about 20% of the galaxy, the other 80% you can't see it. Mystery component number 2. All right, we got matter, and we got this dark matter stuff. If some of it is matter, and a lot of the rest is dark matter, then still isn't enough to take care of the total density. So the rest has got to be something else. Oh my gosh, what? Well, it can't be matter, which would count for matter. What else has mass? E equals mc squared. Energy. Yes, it's got to be energy. So let's call it dark energy. Now, there's nothing dark about dark energy. It's a fine name. There's nothing dark about it. Though I think the name was caught on because it sort of reflects the dark matter name. But I think it's a good name because it does reflect the our darkness, our not knowing what it is. Though Sean Carroll used to be at the University of Chicago and is now at Caltech, has done some of the good work on this. In a footnote of one of his papers, he suggests an alternate name. He says we call it smooth tension. And he says it's smooth, it's everywhere in the universe. It's thought to be evenly distributed everywhere. And it's a tension. I mean, what the cause isn't quite the right word. The manifestation of this energy is a tension pulling in on the universe. So as the universe expands, it affects the way the universe expands, et cetera, et cetera. So he said there's 2 reasons why his name is better than dark matter. 1, smooth tension is actually more accurately descriptive than dark energy. And 2, it's a lot sexier name. He says it right in the footnote of the site. A man after my own heart. So here's the current consensus. About 4% of the universe is matter, atoms, stuff like tables and students and stars. And about 24% of it is dark matter. Kind of matter, we don't know what it is. And we know even less about the 70%, which is dark energy. That's the current consensus. The assessments of the current consensus, People have been looking for dark matter for decades. They haven't found it. Every once in a while, someone says, I think I found it. Someone else checks. Nope, you didn't. No, you didn't. Concerning dark energy, I love the quote by Michael Turner at the University of Chicago, who some of the faculty here will remember he was the speaker at Shimer's graduation in the late 1990s, 98 or 99, I think. He says, understanding dark energy is the most profound problem in all of science. Wow. Why so profound? A, you have hardly a clue what it is. That makes it a really intriguing problem. And B, the best estimate of it is a little bit off. I mean, you can estimate how much there should be based on theory. Before I can take you there, I have to give you a little bit of background. Quantum field theory in a thimble. We want to measure dark energy is what? Well, the weight of empty space. What? The weight of empty space. How can space weigh? How can empty space weigh something? Damn it, because it ain't empty. The vacuum is not nothing. It just has no particles in it. Net side one, Aristotle's physics. No void. The guy was right. We just had to discover quantum field theory to realize it. Space is, in fact, filled with fields. So even if you take out all the particles, atoms, electrons, even the photons, you still have fields. Not nothing. You know, a field is the sum of all the quantum components or oscillations at all points in space. That actually should sound familiar to anyone here who's had natural sciences. Feynman in QED basically says, what happens? You take all the possible things which could happen at all of the points in space, you add them all up, and what the sum is what actually happens, right? That's quantum field theory. That's what QED is. The interesting thing is, each of those oscillations that we're adding up contributes a little bit of energy, which you've also seen in exercise 4, Planck's law. E equals h nu. Energy equals Planck's constant times frequency. So, for a quantum field, here's how we pronounce that. Psi equals the sum of e to the I times the quantity kx minus omega t. You say, what the heck is that? Anyone in the room with a physics or engineering background immediately is spotting what that is. That's the symbol, or that's the expression for a wave, a sine and cosine wave. Before I go any further, beautiful or not beautiful? I think it's real beautiful. It's extremely simple, and basically, all the world is made out of fields, and this is what the fields are made of waves, expressed very simply. And you just have to add them all up, which is what the sigma sign means. And one other thing, you might say, wait a minute, I had some math. I remember exponentials. That's the function where the curve goes up, it keeps going up and up faster and faster and faster. That sound familiar? And that is what exponentials do. When they're taken to the power of a regular number. But when taken to the power of an imaginary number, I is an imaginary unit, then it doesn't go up. It goes like this. And you want to know why? Because mathematics is magic. Okay, so, and that is why that equation is beautiful, because mathematics is magic. The energy of the vacuum, we sum up all of these oscillations. The net calculated energy, if we sum up all of the possible oscillations that we know of, we get a density of 10 to the 92nd grams per cubic centimeter. Can anyone here spot a problem with that number?
That's huge.
That's a big number. Very good. The density of scientific notation, if you don't know that, I'm sorry, I failed you. But if you do, I'll point out, the density of water is 1 gram per cubic centimeter. So that's 10 to the 0. the density of lead is about 10 to the 1. The density of a neutron star is about 10 to the 15th. So according to quantum field theory, the density of empty space should be trillions and trillions and trillions and trillions of times denser than a neutron star. Observation tells us that's incorrect. And the first rule of science, experiments trump theory. There's something wrong. It's a little bit more. The real value of rho of the vacuum, the density of empty space, is 7.2 times 10 to the minus 29 grams per cubic centimeter. So the theory is wrong by a factor of 10 to the 127th. Or as I like to point out, 10 to the 124th percent. This is where I come in. My grand obsession started with what the heck is going on? I actually started with dark matter, but let me talk about dark energy first. My view is that dark energy is a quantum phenomenon. Fellow physicists don't argue with me on that one. All we need to do is take quantum mechanics and general relativity, and we can solve it. Unfortunately, no one can figure out how to do that because it's currently formulated. The two are mutually incompatible. There are some very brilliant minds trying to find theories of quantum gravity, if you've heard that phrase. If anyone finds a theory of quantum gravity, what I've been working on is probably a homework problem. But no one can do quantum gravity yet, and no one even knows how to do it yet. So I'm compromising. Not with a full quantum field theory and general relativity theory. My compromise is do quantum field theory more or less the way that gave that previous number, but simply take into account that the universe is expanding without having to bring in all the aspects of general relativity at once. It's not a perfect, it's an approximation. It's not a perfect model. Let's see where it takes us. Well, in general relativity, time and space are related. In an expanding universe, distance is stretching with time. Well, if distance is stretching, the measure of space itself is time dependent. And that's what no one has, as well as I can tell in the literature, no one has taken into account. They say, okay, we'll deal with the space aspect, we'll deal with the time aspect, without realizing, when we're dealing with the space aspect, we can't make out the time. We gotta do them both at once. So I did them both at once. The fact that you're stretching the space, the space, the distance component, adds an additional energy component. Because the quantum oscillations are stretching. The energy of the stretching exactly cancels the energy I showed you earlier. So when you take the energy of standard quantum field theory plus the energy of the stretching metric, the density of empty space is 0, which is a lot closer. And what if you didn't think like a physicist, you'd say, well, that's the right answer, but it's not the right answer. So I want to deal with, okay, 0 is not too small. How do we get to that number 7.2 times 10 to the minus 29? Well, here's the next thing I do. I take into account that the universe has a finite age. Big, it's old. It's older than me. But it's still finite. Since it's expanding, we know it had a beginning, because if you shrink it down, run the movie backwards, eventually it goes down to 0 size. We'll call that time 0. Official name for that is the initial singularity. Singularity because if you try and fit all the rest of the universe in a very small space, that's hard. You try and put it in 0 space, well, now wait a minute. Density goes to infinity. That doesn't make sense. The term singularity means, hey, this doesn't make sense. Well, that's a mathematical term for this doesn't make sense. Now the universe is 13.7 billion years old. That affects the vacuum. I make one assumption, that everything observable by us is in the observable universe. No one has ever called me on that assumption. Put in physics terms, any wave function has to go to 0 at the initial singularity. That probably doesn't help you much. Let me give you a picture. Here's an oscillation. Let's call it a wave function. Versus time. And on this time graph, which covers a lot of time, the Big Bang, let's say, happens here, and here's now. What I'm saying is, I can't talk about this. I have no idea if there even is a before the Big Bang. So I have to cut off any wave function here at the Big Bang and throw everything else away. I'll call it 0. That's all I do with mathematics. That's my theory. When I do that, I chop the wave. It affects the spectrum. I get harmonics. When I mean spectrum, I don't mean the rainbow, but you probably are familiar with the idea of a sound spectrum, like you see on your MP3 player. It shows you the bass, the treble, and so on. I get harmonics. The harmonics are new frequencies. They added increments of energy. The main harmonic is the age of the universe. In pictures of this perfect sine wave, here's the one frequency. I chop it, I get harmonics. These guys now add additional components of energy. Gosh, I wonder how much. Well, equals h nu. H is very small. The frequency is 1 for 13.7 billion years. I'm a bass player. I know I can't play a bass note that long. That's a low frequency. So we got this small number divided by this big number, and we get an energy from one of those harmonics of 10 to the minus 52nd joule. Those of you who know scientific notation are probably thinking, oh, come on. To put that in perspective, my wallet is about 250 grams. So if I drop it from here, that amount of energy is about 1 joule. Each of these harmonics is 10 to the minus 52nd power, that much energy. Sounds like 0, doesn't it? But it's not 0, it's just really, 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 really small. And it's not 0 is important because we're dealing with something which is mind-bogglingly big. So you multiply a really small number by mind-bogglingly big, you might get something. Sure enough, you do. I add the energy for each component. It's small but cumulative. I add them all up over all the space in the universe, over all the oscillations. The energy of the vacuum that my hypothesis suggests is 5.5 times 10 to the minus 29 grams per cubic centimeter. I'm off by about 20%. The other guy's off by 10 to the 124th%. I don't feel bad. Now let me finish up with dark matter. From what I said before, dark matter is inferred from the rotation of galaxies. You know, they're rotating faster than we expect. What if something else accounted for it? What if it wasn't dark matter? Here's the rotation, as I described before. This is rotating faster than we expect. That's the curve we expect from Newtonian mechanics. Something is causing that faster rotation. Could be dark matter. Maybe it's something else. Here are some hypotheses. None of these are mine. The two main classes that have been proposed for dark matter is that maybe it is some type of exotic matter, generally referred to in the literature as WIMPs. The alternative is, no, they're real small objects that are too dark to see, like brown dwarfs and pale stars and burned out stars and stuff. Those are called machos. I am not making this up. WIMP is an acronym, weakly interacting massive particles. Machos are massive compact halo objects. So, according to the two leading contentions about dark matter, either most of the matter in the world is wimps or machos. I don't like it. An alternative that has been suggested is no, let's adjust Newton's laws to fit the data. This is called MOD for modified Newtonian dynamics. This is the, let's see, of these three alternatives, this is the least commonly accepted in the scientific community. Wimps are the most, no jokes about physicists, and machos is in between. I presented these three to a group of Shimer students on the last day of Natural Sciences 1. Since Nat Sci 1 is, what is the world made out of? I could on the last day present some articles, Scientific American type things, based on those three ideas, in which we could discuss it in real time, where for a wonderful session of Nat Sci 1, no one could turn to me and say, what's the real answer? Because I didn't know any more than anyone else in the room. So what was great about it is the students, God loves Shimer students, they picked apart these theories beautifully. They didn't buy any of them. They could see the holes in all three proposals. When I threw out an idea, which I no longer think is right, I've gone beyond it, but I threw an idea, what about this? And they said, wow, that's a really intriguing idea. We explored it, and God loves Shimer students. They didn't say, well, you're the teacher, you're right. They said, we prove it. I couldn't at the time, but I said, damn it, I'm gonna. And since then, I've talked to physics colleagues, and they said to me too, prove it. You think you got a good idea, prove it. Show me the math or go home. And after that, show me the data. Well, I've been working on the math. But what they pointed out to me, and were very critical of it, some of them, is that, Jim, you're confusing things. You're using the wrong tools. Quantum mechanics is for small things. Classical mechanics is for big things. General relativity is for really big things. And the general feeling, and the reasonable one, in the physics community is that large objects are too large to see quantum effects. But I think we're fools. I think we're facing something that Luz de Broglie faced almost a century ago. Nat Sci 4 graduate who's read de Broglie. Can you read that out loud so everyone can hear you?
Then physics was divided into two camps. On the one hand, there was physics of matter based on the concept of corpuscles, atoms, which were assumed to obey the classical laws of Newtonian mechanics. On the other hand, there was physics of radiation based on the idea of wave propagation, the hypothetical continuous medium, the ether of light. But these two systems of physics could not remain alien to each other. The amalgamation had to be effective.
Luz de Broglie, and he wrote that around 1930. I agree with de Broglie. I think that an amalgamation is going to be effective. And here's how I do it. Since I'm crazy enough to do that, I'll say, step one, take the wave function of a star, which sounds an extremely difficult problem. It's actually extremely easy. It's been solved. A star moving around a mass behaves quantum mechanically exactly like an electron moving around a proton. The solution to the hydrogen atom in the first month of a quantum mechanics course. So I'll take that wave function, I'll truncate it, just like I showed you that I truncated before, and that's going to give me an extra energy, just like before. Only this time it's an extra energy, not of a vacuum, but of the orbit of a star. So I'm bold enough to suggest that these things out here are, the motion is primarily a quantum mechanical effect, not a classical gravitational effect. Rather than show you what I was doing before, which is the formal name of what I was doing with the spectrum and the chopping and the waves and stuff, is called Fourier analysis. I'm going to use the Heisenberg uncertainty principle, because most of you have heard of it and have a sense of what that might mean. It gives an only approximate number, but I think that gives you an alternate way of looking at it, and you might get a feel for it. Uncertainty. The uncertainty in the action of any particle is greater than Planck's constant over 4 pi. That means nothing can be totally still. There's a minimum possible energy. And from the uncertainty principle, this looks familiar, somebody to see it, and that's I forward. The uncertainty in momentum times the uncertainty in space is less than h over 4 pi. Incidentally, though most people don't look at it this way, this is equal to the uncertainty in energy times the uncertainty in time. And this leads, the fact that you can't know exactly the momentum and exactly the location at any time leads to the old physics joke of Werner Heisenberg being pulled over for speeding on the Autobahn. And the cop gets out and says, "Oh, Dr. Heisenberg, do you know how fast you were going?" He says, "No, but I know exactly where I am." Now, because the uncertainty in energy is inversely proportional to the uncertainty in time, the maximum possible value of delta t will yield the minimum possible value of delta E, a minimum energy. Well, the largest possible time in the universe, 13.7 billion years old, is 13.7 billion years. Once you take that into account, you get a minimum energy, which is very close to the same size as what I showed you with my formal calculation before. It's a very small energy. And then the energy of a star is the classical energy plus the sum of all of these tiny little minimum energies. This is the formula for the classical. And then you take the quantum number times the minimum energy. It turns out that when you get far enough to the edge of a galaxy, this is a bigger chunk of energy than that. Because you're so darn far away from the middle of the galaxy that the gravitational energy is so close to zero. And the quantum energy, which increases as you go further out, this starts to dominate. And it makes the star move faster, just like dark matter is supposed to. Hey, fine. That's qualitative. Scientists want graphs. Well, here's a graph. This shows, this is a theoretical calculation. This is the amount of energy, or I should say the velocity you would expect for classical movement of a star around the galaxy. It's the same scale as I showed you with that other graph. This is the minimum energy contribution. This is them summed together. Does that look kind of familiar? Oops. Oh, wait, no. Here's the middle. I have lost my place. Just take a second. Talk amongst yourselves. The data that I showed you before, doesn't it? Here's another calculation. The black curves are the rotation curves for galaxies of different brightness. These are big galaxies. These are pretty small galaxies. The black curves are data. The colored curves are theory, based on my theory. This fits pretty good. I'm proud of that. So I think that the motion of galaxies is accounted for completely, or almost completely, is suppose, the data can tell me, by this idea that there's an extra energy caused by the truncation of the wave function. Which, if I can explain it without having to invoke the mystery of dark matter, my belief is there is no dark matter. Now, I don't know that there's no dark matter for two reasons. One is I may have made a mistake. So I say everything is tentative until I get this published in a peer-reviewed journal, because the burden of proof, NANSI 3, we just went through it. Newton's rules for reasoning. The burden of proof is on the new idea to prove itself, not on the new idea to say, well, you're going to prove me wrong. That's cheating. No idea you're going to prove yourself. I haven't done it. So we'll see what my colleagues say when I submit it for publication. But even then, that's not enough. Because in the end, data wins. And so I won't be satisfied until I or someone can do critical experiments which can tell me if I'm wrong. If I'm right, then the velocity in galaxies should not only level off, but should increase when you get really far away. Most people don't look really far away. So I'm going to encourage colleagues to look very far away on very large galaxies. There's some other systems where it could be studied as well. Another idea is galaxies very far away. The light came from them billions of years ago. The universe was younger, less time. The minimum energy should have been larger back then. They should be spinning faster than galaxies closer to us. I'm not aware of any data in that, so I'm making a prediction, putting myself on the line. Maybe someday can prove, maybe someday somebody can prove if I'm right or wrong. So in summary, what is the what in the world? About 4 to 5% of it is matter we can see. Stuff like that. Even if I can't kick it, like the air. Second, we see an extra tug in rotating galaxies. The current common view is to infer dark matter exists from that. My work suggests that there is little or no dark matter. And finally, we see from the cosmic microwave background that space is flat, and we know that the expansion is accelerating. From that we can infer dark energy, which I believe does exist. And my work suggests it has a quantum source. Beautiful or not beautiful? Beautiful or not beautiful? Hey, not just physics, we can have beauty in meteorology too, can't we? Even, that's one of the most perfectly formed hurricane eyes I've ever seen. If memory serves me, that's Hurricane Hugo, shortly before it hit North Carolina. Within about a day, that thing back in the 1990s, that is about to create more damage and havoc of any hurricane to that date that hit the U.S. mainland. The scary thing is, nonetheless, it's beautiful. Terrifying, but beautiful. And I'm not even going to stick to the physical sciences. How about in the biological sciences? Any fans here of XKCD? All right, XKCD. Leo, where are you? Can you read that?
I can read it. Problem with science is take the wonder and beauty out of everything by trying to analyze it.
Dude! My plasmoidal slime molds have heightened pigment production. Check out that yellow color. That actually makes them zinc resistant. Amazing, huh?
Looks like dog park.
Yeah. Fatica simpatica is nicknamed dog vomit slime mold. Cool, huh? Check out my slides.
Okay, never mind. What's wrong with science is the juicy wonder and beauty and everything. God.
It wants to hug you. Oh, that's so cute. That's simpatica. I want you to see it in person. Now the hard question. Beautiful or not beautiful? Beautiful? will remind you that in Parts of Animals, Aristotle points out that even the lowliest of organisms has its own dignity and is worthy of study. Because if you think about it, slime holes are really weak. Oh. It basically is like living snot that crawls along the ground. But it's alive. That alone is so amazing that I think it's beautiful. It's also a great color. So what am I going to do all of this? Well, I've learned some physics, but I learned a lot more than that being here at Shimer. The numbers and details that I've shown you are new. The ideas are ancient. I mean, among our predecessors, Anaximenes and Empedocles pointed out balance and law maintain the world. Heraclitus, look for the hidden harmony. Parmenides, what is, and cannot not be. Pythagoras, number rules all things. Newton and Aristotle both say, and we read these passages in the core, nature does nothing in vain. Galileo, this we don't read in the core, but my favorite quote of his, numbers are the alphabet with which God has written the book of the world. And most recently, Einstein. The most beautiful thing we can experience is the mysterious. It is the source of all true art and all science. And one thing I've learned, those guys are right. Thank you. The best part isn't the applause. The best part is I don't have to be nervous anymore. Is there time? Do you want any questions? Are there any questions?
Submitting your paper.
What?
When are you submitting your paper?
When I get time to write it. Hey, I'm on 3 committees. I'm on 4. And currently, any writing time I have goes into the self-study. But if I don't get time by the end of the semester, winter break. I'll do writing over winter break.
Where does antimatter fit into the percentages that you wrote down?
Antimatter would fall under the 4 to 5%, which is matter. And the official, I refer to it as atoms just because people have an idea what an atom is. The official name for this class of matter are called baryonic matter. Anything made up out of basically quarks and electrons, neutrons, protons, antineutrons, antiprotons. So antimatter would be considered part of the 4 to 5%.
I just have a question about the galaxies appear to be rotating. We're talking about the stars at the end of the galaxy rotating at a faster rate.
Faster than expected, but still not, well, yeah, just faster.
Well, that's my question. I remember from IS2 we looked at records and how records spin around and how you have the smaller grooves on the inside sort of keeping up with the larger grooves and how that was kind of funky to think about something traveling at the same speeds but going at a longer distance. Is that, I'm trying to picture that
It's a good
rotation
analogy.
of the galaxy and
The-
how that all works.
Yeah, that's a good analogy. The rotation, let's say, I'll go back by analogy to the solar system, which is what people expected to see as a type of behavior, is fast in the middle, Mercury going around every 88 days, Earth every year, Jupiter every 12 years, Pluto every 260 years, slower as you go out. Galaxies actually are more like records. The outside is traveling almost as fast as most of the way in, and that's what blew people away when they first saw that 3-4 decades ago.
So when you see these spiral galaxies, it's not like they're spinning apart. They're always, are they always going to stay cohesive like that, or do we expect the stars to sort of start trailing on?
More or less cohesive. It depends on all sorts of details, but on average, more or less cohesive. More or less as a unit, yeah.
So then the spirals of light have to do with the rotation of, there's like some rotation
The short answer is the spirals stay in place as they rotate. If your question is what causes the spirals to begin with, that's I'll discuss it afterwards because there are a few ideas and it's not a short answer.
Well, I don't know how to word this quite, because I'm not really familiar with the subject matter.
Shimer students are good with words, go for it.
Okay, so you're talking about how once you get further out, quantum mechanics and classical mechanics are that sort of different relationship. Is that what you're saying? Like, when you get further out, what was
The usual picture of physicists is that classical mechanics is the best way to describe anything big, and by big, anything much more than an atom. So I mean, you would be really big, a bacterium would be big. Imagine how big a star or galaxy is. And so the usual view is, once you get outside of atoms, it's all classical. I'm suggesting that the classical effects are all there, of course, that the quantum effects are always there in you and me walking around the room. You know, do you see me vibrating like in a wave function? No, because the vibration is so small. But in what I'm suggesting, I should be more precise, what my model leads me to conclude is that when you get a star really, really far from the center of the galaxy, there's sort of two things going on. One is there's almost nothing else affecting it. It is so far away, even from the mass of the galaxy, that any small effect will probably be visible. But secondly, the small effect of the quantum the small effect of this minimum energy is magnified because it's cumulative. It's actually greater the further away you get from the middle. And so when you're real far away, the quantum effect is bigger than the classical. When I'm near the middle of the galaxy, the classical is bigger, the quantum is smaller, and so you really don't see it. Is that addressing your question?
Yeah, because you were saying that it's kind of like you have, when you're saying that space is bent like that, like there's places where there's a lot of mass, like galaxies, and that's causing something to bend.
The issue of bending space is how I would explain gravity, and it's not directly a part of this quantum effect. That I would just say, we can talk about bending the space more simply for now. We'll talk Newtonian gravity and leave it at that. At this point, I'm really dealing with gravity as if it's Newtonian, not as if it's general relativity. I'm doing it simpler. Say, you have a question?
How far is the parsec?
Good. This man has an eye for detail. A parsec is 3.2 light years. So the units on that kiloparsecs were 3,200 light years per kiloparsec. Why that's a unit is a matter of history. We can discuss it after.
I'm curious as to whether the light reaching us versus what's actually going on has any bearing, or does because we see what happened several hundred years ago with telescopes. Does gravity move at that same speed?
Gravity moves at the speed of light, yes.
Okay.
And it's an interesting question which I didn't deal with here, but it's a very key thing that astrophysicists have to keep in mind when they're dealing with a problem. I look out in the telescope, I see something a billion light years away. Technically, I see something a million light years away, but the effect is much less. A billion light years away. I see where it was a billion years ago. That's not where it is now. It's somewhere else. So, for certain calculations, you have to take into account that not only has it moved, but the universe has expanded while it moved, and then at certain levels of complexity. For here, actually, implicit at one point of the calculations that I didn't show you, I do account for that. More questions?
I wonder if you could talk a little more about your assumption of truncating.
Truncating, yeah.
Yeah, I guess, I mean, if I can get it completely wrong, but basically you're assuming
puzzle here. And by the way, the word truncate is familiar to some people, not to others. Truncate, chop off. That's why we call it a tree trunk, because we truncated the tree. Okay? It isn't so much that I assume that the energy is zero before the Big Bang. For all intents and purposes, the way I deal with the mathematics, the way I deal with physics, is I assume that there is nothing at all. There's no wave function, there's no energy, there's no time, there's no space, there's no nothing. Now, as to whether there was, I don't even know if that's a meaningful question. It would be like asking, well, you know, what would my younger brother be like? I'm the youngest of 4 children. I have a big brother. So to speak of something which does not and never did exist in time, I don't know what to say about it. I feel the same way about before. So all I do is I just say, I go back to the beginning and I say, whatever, I don't even pay attention to it. My personal view is it's meaningless, and I agree with St. Augustine. Space came into existence, time came into existence at the same time. You can't even speak of time before. Am I addressing your question?
Yes, I was also curious how you relate that to the first law of thermodynamics.
Well, there's Stephen Good, who's on the faculty at MIT, was the guy who developed what's called the inflation theory, which I'm referring to in my 3rd slide. A period right after the beginning, I mean, in the first microsecond, where the universe very suddenly expanded. He has an interesting phrase. He said, it looks like the universe is the ultimate free lunch. Because if you take the laws of physics and say, okay, if it expanded the way the laws of quantum mechanics suggest, there was a force that would be felt. And that force that would be felt, which is just the energy of space itself, generates work as it expands, and work is energy. So that in fact, it isn't like energy was created out of nothing, it's work it's force times distance. It's following Newton's laws. And it appears that, here's the formal way of putting it, the potential energy, the gravitational potential energy of matter is exactly equal to the energy of the matter itself. So that the net value of energy in the universe as a whole is 0. A free lunch. Not everyone thinks the numbers work out the way he says. So you might say, gosh, where's all this extra energy coming from? It's sort of like an accounting trick. If I take $1 out of this pocket, put it into this pocket, I'm neither richer nor poorer, but I got more money over here. I'm going to call this one matter. I'm going to call this one potential energy. That's what some people think is going on. I know it sounds weird. That's what the equations are telling us. And any more questions?
Does your equation explain cosmic lensing?
No. And not so much, how do I want to put this? Cosmic lensing doesn't need me. I mean, it works, if you take general relativity, cosmic lensing, oh wait, I think I've taken the implication of your question. Let me break your question into 2. Cosmic lensing as a phenomenon is pretty well understood and can be calculated using general relativity. Certain forms of cosmic lensing are attributed to dark matter.
Yes.
The short answer to that is yes, it can, because you would expect an additional, what's the word I want to use, an additional bend in a geodesic, in the light's path, as it moved through the edge of like a galaxy. So the lensing which has been attributed to dark matter could be accounted for by this. I haven't done the detailed calculations myself. But the short answer is yes. And in fact, the claims where people have said, oh, we've actually mapped dark matter, like in this cluster or in these galaxies. Those are done using gravitational effects. And any gravitational effect will be affected by this extra minimum energy. And so it'll so can account for it. That's such a subtle question. Can you talk to me afterwards? You obviously know some physics.
Yes.
Good. Thank you.
Let's thank Katie again. Dr. Donovan will be doing a second program that will follow up this program on Wednesday, October 19th at 6 p.m. at the Shimer campus. If you're interested in attending this presentation, which will be a much more scientific and technical explanation of his research, if you refer to your program, it gives you the contact information for Aaron Garland, and you can RSVP, and we will provide you information as to the exact location. The next program in the series is 2 weeks from tonight, here again in the NTCC auditorium. We are pleased to welcome Dr. Carol Adams, the CEO and President of the DuSable Museum of African American History, who will be presenting on changing demographics in the neighborhoods here in Chicago. Again, thank you for coming this evening, and let's adjourn next door for some refreshments and informal conversation.